Welcome to Module 2. In this module, we will be solving systems of linear equations. And the first thing that we're going to do is look at the Gauss-Jordan method. So by the end of this video, you will be able to solve a system of linear equations by hand using the Gauss-Jordan method. Okay, so why do we care about systems of linear equations? It's because many engineering systems can be described by such systems of linear equations. So here is just an example, basically from math. Right? We have three unknowns, x1, x2, x3, that can be determined as the solution of three linear equations, as shown here. So how do we get these individual equations? Well, they come from models, for example, from physical models. They come from your mechanics class or from your fluid dynamics class or your thermodynamics class. They basically come from physical descriptions of the real world that we're trying to solve when we're doing engineering applications. So now the system of equations written up there can be written in a shorthand using matrix notations, which you should be familiar with from linear algebra. So the coefficients that multiply the unknowns x1, x2, and x3 can be written inside of a matrix, where each row of this matrix corresponds to one of the equations up here. So the first row here, you can see the coefficients. The coefficient 1 multiplies x1, the coefficient 2 multiplies x2, and the coefficient -2 multiplies x3. And the right-hand side is given as a right-hand side vector, the first row of that vector being equal to 9, because that's the right-hand side of the first equation. Now, from linear algebra, we can write this in a shorthand way using a vector, an arrow on top of a vector. We can write the matrix A times a vector of unknown values x is equal to a given right-hand side B. And if we want to solve this, this becomes really easy in linear algebra, because I can directly write the solution, that the solution vector x is equal to the inverse of A times the right-hand side vector B. And the definition of an inverse, if the matrix A is square, is simply that A inverse times A is equal to the identity matrix, and A times A inverse is equal to the identity matrix as well. But of course, it's not that simple if we actually want to know what the numerical values of our solution are. Because in that case, we need to at least calculate the inverse of the matrix. So when we're doing numerical methods, how do we calculate the solution? If the system of equations is small, so at most a 3x3 system, we can use Cramer's rule, which is very practical for 2x2 systems, so two equations with two unknowns. But anything larger than a 3x3 system, for example, if 5 equations with 5 unknowns, Cramer's rule becomes very impractical to do. We could follow the lead from linear algebra. We could try to calculate the inverse of A and then do a matrix multiplication of the inverse of A times the right-hand side vector B. It turns out that that is actually too much work. We can get the result a little bit faster. And that better, faster algorithm that we're going to talk about here is the so-called Gauss-Jordan elimination algorithm. Now, all of these methods that are listed here will give you the exact solution. And exact here is in quotation marks, because we know that when we're dealing with computers that we will always have round-off errors. So up to round-off errors, these methods will give you the exact solution. And these methods are called direct methods. There are also so-called iterative methods that we will not cover in this class. Those methods are applicable to very large systems of linear equations, where we then won't know the exact answer, but we will know an approximate answer. But that will be covered in other classes. Okay, so let's do an example. Before we do the example, let's actually talk about the Gauss-Jordan elimination algorithm. It's a procedure to solve non-singular systems of linear equations. And here are the individual steps. The first step is to concat the right-hand side to the matrix A to arrive at the so-called augmented form. And we can use this algorithm to solve a system for multiple different right-hand sides. So that's why there is the option here of the plural for right-hand sides. Now the algorithm says that for each diagonal entry, we call these diagonal entry pivots, in the matrix A, we will do the following steps. We will divide the current pivot row of this augmented matrix that we generated by the value that we find in the pivot position. And then for each row other than the current pivot row that we're working on, we will subtract a multiple of the pivot row to generate a 0 in the pivot column. And after we've done this for each pivot, we will then have the solution to the system in the last column or columns of the augmented matrix. Okay, so let's do an example. Let's solve these three linear equations for the three unknowns x1, x2, and x3 using our algorithm. Okay, so let's put the algorithm here on the top of the slide. Let's just walk through them one by one, through the steps one by one, and see what happens to the matrix and the solution. Step one was concat the right-hand side that this system has to the matrix A to arrive at the augmented form. So I'm going to take the matrix A and I'm going to copy it on the left of the augmented form, and I'm just going to take the right-hand side. In this case, we only have one right-hand side, and I'm just going to add it as an additional column to the right of the original matrix A. If I had multiple different right-hand sides, I would just add additional columns for these different right-hand sides to this augmented matrix. And this combination of the matrix A and the right-hand sides as additional columns is called the augmented matrix form. Okay, so next up is for each diagonal entry, which we call pivots, in the matrix A, we're going to do the following steps. Okay, so here is my first diagonal entry, which is the number 2. I'm going to divide the current pivot row, and I'm working at the first pivot, so my current pivot row is row number 1. I'm going to divide this entire row by the value in the pivot position. So I'm just going to divide this entire row by the number 2. Okay, so what do I get? If I divide this first row by the number 2, I get 2 divided by 2 is 1, 4 divided by 2 is 2, negative 4 divided by 2 is negative 2, and 18 divided by 2 is equal to 9. And now I'm just simply copying the other rows of this matrix over to my new augmented form because I don't really want to do anything with those rows yet in this one step. Now, next up is for each row other than the current pivot row, so other than the current first row, I'm going to do something. I'm going to subtract a multiple of the pivot row to generate a 0 in the pivot column. So what I want to do here is I want to generate the number 0 right here. And I want to do this by subtracting a multiple of the first row from my current row 2. So I have to figure out what is the multiple for row number 1 that I want to then subtract from row number 2 to generate a 0 here. So row number 1, my pivot row, there's a 1 here. And I want to make this 2 into a 0, so I have to subtract 2 times 1 from this row, right? So the multiplier seems to be the entry here that I want to make 0. Okay, so let's do this, right? So I want to subtract 2 times row number 1 from row number 2. But I'm not going to do anything to the first row, right? That was my pivot row. So I'm just going to copy that over into my next intermediate step here as my first row. And now I do my operations on the second row, and I generate the 0 there. So I'm going to take 2 minus 2 times 1. That is the 0 that I wanted to have. Next up is 3 minus 2 times 2. So 3 minus 4, that's negative 1. In the next column, I have 1 minus 2 times negative 2. So that's 1 plus 4. That's equal to 5. And then finally, I have 23 minus 2 times 9. It's 23 minus 18. That's equal to 5 as well. Okay, so I have worked now on the first row that is not the pivot row, and I can move on to the next row that is not the pivot row because I have to loop here over every single row that is not my current pivot row. So that would put me into my third row here. And now I have to try to generate a 0 here underneath my current pivot. Right here I want to generate a 0. So the question is, what is the multiplier for row number 1? That if I subtract the result from row number 3, I will get a 0 in this position. Well, that multiplier is the 3 that is right there, right? Because I first turned my pivot into a 1, so therefore to generate the 0 here, my multiplier is exactly this entry that I want to turn into a 0. So my operation now is take the row number 3 and subtract from it 3 times row number 1. So 3 minus 3 times 1, that's 0, the 0 that I wanted to generate. Next up is 2 minus 3 times 2, so 2 minus 6, that's negative 4. The next column is negative 4 minus 3 times negative 2, that's minus 4 plus 6, that's 2. And then finally I have 11 minus 3 times 9, it's 11 minus 27, that's negative 16. Okay, so now I have done these operations for each row that was not my current pivot row. And now I can go up again to the second step of the algorithm where I had to do something for each diagonal entry. So I did all my operations for the first diagonal entry, so I can move now on to the second diagonal entry. And that diagonal entry is negative 1. And the first step that I have to do is I have to divide this current pivot row, the second row, that's my current pivot row, by the entry in the pivot position, which is negative 1. So I have to take this entire row and divide it by negative 1. I'm not going to do anything to the first row here, so I'm just going to copy this over. And now I'm dividing the second row by negative 1. So I get a 0 and a 1. Then I get 5 divided by negative 1 is negative 5. And again, 5 divided by negative 1 is negative 5 again. And I'm not going to do anything for now with the third row because that's not my current pivot row. So I'm just going to move that over and into my intermediate result here. Good, I'm done with that step. And now again, for each row, other than the current pivot row, so other than my current second row, I will do the following steps. Subtract a multiple of the pivot row to generate a 0 in the pivot column. Okay, so this is my pivot here. My pivot column is the second column. I'm going to start with the first row, so row number 1, that's not my pivot row, so I have to try to generate a 0 right here in this position. And I do this by finding the multiplier for my pivot row number 2 that I then will subtract from row number 1. So that multiplier again has to just be this entry that I want to make 0. So the multiplier has to be a 2. Okay, so let's do this. Let's take row number 1 and subtract 2 times row number 2 from it. So we get 2 minus 2 times 1, that's 0. And the 1 in the first column here sees a 0 below it, so nothing will happen to it. So I can just copy that over. Next up is, I'm going to do negative 2 minus 2 times negative 5. So that's minus 2 plus 10, that's 8. Next up is 9 minus 2 times negative 5. So 9 plus 10, that's 19. Not going to do anything in this step with the pivot row, so I'm just going to copy this over into my intermediate result. And I can move on to the last row here, where I now have to try to make a 0 in the -4 position. And we already saw that that multiplier that I have to multiply my pivot row by to generate the 0 is simply the entry that I want to make 0. So that multiplier then is -4. So let's do this. Let me take row number 3 minus -4 times row number 2. Okay, so let's do the operations. I will get a 0 in the first column. I get the 0 that I wanted to generate in the second column. And now I have to do some math for column number 3. That would be 2 minus minus, so 2 plus 4 times -5, so 2 minus 20, that's -18. And then in the last column I have -16 plus 4 times -5, -16 minus 20, that's -36. All right, I've generated the 0 in the pivot column for every row for the second pivot. So now I can go on to the last diagonal entry, which would be in the third row. That's the -18 here. And the step that I have to do is I have to divide that current pivot row by the pivot entry. The pivot entry is -18, so I have to divide this third row by -18. Okay. So I'm not going to do anything in this step for the first 2 rows, so I'm just going to move them over into my intermediate result. And now I'm going to divide the third row by the pivot entry, -18, so I get 0, 0, -18 by -18 is 1, and -36 divided by -18 is just 2. Good. Now I have to do for each row other than my current third pivot row, I have to generate zeros in that column by subtracting a multiple of the pivot row from that corresponding row. So let's start out with the first row. I want to find a multiplier of row number 3 to generate a 0 where the 8 currently resides. And that multiplier we've seen already has to be that entry itself, so the multiplier is 8. Okay, so let's do these operations. So I get the first 2 columns are going to be 1, 0, and then I've generated the 0 here, right? 8 minus 8 times 1 is 0. And in my last column, I'm going to do the operation 19 minus 8 times 2, so 19 minus 16, that's equal to 3. Okay, let's move on to the next row. That's row number 2. I want to find the multiplier for row number 3 that I can subtract from row number 2 to generate a 0 in the -5 position, and that multiplier has to then be -5. So let's do these operations. I will start out with 0, 1, and now I'm generating the 0 in the -5 position in the third column. And now I have to do some math for that last column. I have -5 minus minus is plus 5 times 2, so -5 plus 10, that's equal to 5. And I'm not going to do anything further for my last row, so I'm just going to move that over and copy it over. Okay, so now I've done all of my steps for each one of the pivot entries, so I'm kind of done. And now the solution to the system is supposed to be in the last column of the augmented form, right? So that would be right over here. The entries would be 3, 5, and 2, and I can write this as the solution. The solution vector x is equal to 3, 5, and 2. So that's an application of the Gauss-Jordan elimination algorithm to a matrix system if you do this by hand. And you'll see that this is quite long and tedious to do. So next up, we will develop the code to let the computer do this for us. All right, thank you for watching.